Hello guys, welcome to KY Tech. Today we're going to talk about diffusions. So when will we use the diffusions? We know that MOSFET will have N-type and PMOS. So for NMOS and PMOS, we need to dope the donor or acceptor to a silicon. And this is the timing we'll use diffusions. So first let's go to one page and a brief overview, then we'll go to it by detail. Diffusion. High temperature process that introduce dopant to silicon to form p-type or n-type region. And here's one way to do it. First we have a silicon oxide, then put a PR on it, then get rid of PR for this location, and then do the etching, then get rid of the PR again to form silicon oxide pattern, then they do the diffusions. Reason they don't use PR as a pattern is because PR cannot stand for high temperature during the diffusions, and it will cause contaminations. So for diffusions, several factors will include in the diffusion coefficients. So first, for diffusion coefficients, it is corresponding to the different elements. So different element will have different diffusion rate. Also, it is corresponding to activation energy and also temperature. All of them will affect your diffusion process. And two boundary conditions, including constant source, which is continuously supply of dopant. As we can see here, constant source. The surface concentration will be constant, and if we keep increasing the timing, the distance from the surface will increase with the dopants. So here is the equation for it. So if we got the surface concentration, we got the concentration at the x location, we can know how deep this diffusion will be by the arc function table, and we'll talk about it on the later slide if you're interested. Junction depth is the intersections for the background NB with the profile over here. For constant dose, it's a fixed number of dopant, which means like the dopant at the surface will start decreasing when you're increasing the timing. And also so as we can see in the constant source, the total dose, which is the surface on the profile, will keep increasing because you have constant source. The constant dose will also increase. But if you're in constant dose, then it will be the same. But like the surface concentration and eventually how deep can you be dosed will be affected. Yeah. So that's brief overview for diffusion. Then we'll go to in detail from now. So diffusion is a high temperature process that you can introduce dopant into silicon to form p-type or n-type region. So as we can see here's the CMOS. We can see we have NMOS and PMOS. So the n-type over here for NMOS is where we need to do diffusions. So we'll dopant probably phosphor for n-type and probably boron for b-type. Here's the pictures. We introduce a dopant gas into the chamber, and here's all the wafer, and then we heat up to do diffusions. And there's two processes to do diffusions. First is oxide mass pattern diffusion. They put a silicon oxide, then use PR to etch away this part, or we just put SOG on it and use PR to keep this part. And here this is like SOG will keep having the dopants from this location on the SOG. Then we'll have a dose get established. Then we'll do annealing to make it go deeper. So for diffusion, we need to talk about fixed first law. So we can know fluid is affected by diffusivity, and also it is affected by dopant concentration, which is N over here. Also, diffusivity will be affected by diffusion coefficients over here, which is corresponding with different element. Also, it is strong correlation with temperature and also the activation energy. So why is diffusion coefficient important? Because we can see over here, for sodium, the diffusion coefficient will be really large, which is easy to do a diffuse, and it will cause contaminate on our tool easily or on our wafers. So there's two boundary conditions for diffusion. First is constant source, which the surface concentration is almost a constant. Or constant dose means that only the dose is constant. Surface concentration will not be constant. Let's go for constant source first. So the longer time or higher diffusivities will yield deeper diffusions. So longer time will be T, and higher diffusivity will be D1. So we can see since it's constant source, so the surface concentration will be constant. And then while we increase even either T or D, we will have a deeper diffusions, and the dosing will be increasing with the timing. Junction depth will be the NB, which is background, with the profile intersections. This. So here's the equations. We can see if we have the surface concentration and the concentration at location X, we can get how deep can we do the diffusions by getting all data and put it back to the arc function table to get a result. So let's talk about total dose. So total dose basically is the area under the profile. So this is constant source. We can see if we increase in the timing or we increase the diffusivity, the surface concentration won't change, but we'll see the dosings will keep increasing. However, for constant dose, since the only constant will be dosings, so the surface concentration will decrease while you increase the timing. And while you increase the timing, we'll also get deeper diffusion also. And here's the equations for the constant dosing. And there's another concept is masking diffusion. So we can see in this process, we first get a silicon oxide, then we'll put a PR, then we etch away the silicon oxide over here. Then we'll get rid of PR. And then we use silicon oxide as a mask to do a diffusion. That's because PR can stand for high temperature and will be a burn and will contaminate our wafer. That's why we use silicon oxide as a mask to do a diffusion. And the next thing we're going to talk about is a 4-point probe. So in here we can measure the sheet resistance, but why we need to measure the sheet resistance is because we can get some important data from this graph. Here on the x-axis is sheet resistance times Xj, which is a depth for the diffusions. And here is surface concentration. From those, we can get NB, which is a concentration at location Xj. But how do we measure sheet resistance? We use 4-point probe to do a measurement. So the outer 2-point probe will measure the current. The inner 2-point probe will measure voltage. The reason we use 4-point, not 2-point, because if we use 2-point, we will measure the contact resistance, and that's not what we want. So if we get a voltage and current, we can get a sheet resistance, and to get more information by this graph. And that's all for it. Thank you.